There we go. I understand the last time you talked about chairs, and I don't know if Nate told you the grown, nerdy OChem dad joke that you can identify fellow classmates with at parties or concerts. It's like your secret catchphrase. And the question that you ask is, what is the opposite of a chair? And then the answer is the other chair. No, it wasn't even, it's not even worth that, it's not even worth that response. So that's sort of how it goes. You've learned about chairs and chair flipping. I want to make sure you're prepared for what you're going to experience on an exam. I've seen students make this mistake again and again, and they come to my office and they say, I thought I understood this, what did I do wrong? And then I show them this, and then they say, oh, right, that was tricky. So I'm disclosing my evil scheme to you in advance so that you can be prepared to thwart me on the exam. Like Doofenshmirtz, nothing would thrill me more than to be thwarted by you, the platypus agent. So I don't know why I'm on a Phineas and Ferb kick. It's normally Star Wars references, but I just got to say what comes out. So look at this molecule. This molecule is called beta-D-galactopyranose. I've drawn it in an overhead view, but there is a six-membered ring there. Though one of the atoms is an oxygen, you can draw this molecule in a chair conformation. Now, if all you've done is memorize axial is less stable than equatorial is more stable than axial, and you read this question and you fixate on most stable, you might be inclined to draw on your sheet of paper, oh, this is easy, I got it. I'm just going to make everything equatorial because equatorial is more stable than axial. The problem here is that in doing that, you have not drawn the correct molecule. It's wrong. It's not. Is it the most stable chair of that molecule? No, because it's not even the right molecule. So let's talk about how and why it's not the right molecule. The easiest way to see this is if we start numbering the atoms of the ring, and one by one, go around and decide whether from this point of view, looking down on the molecule from above, the substituents on the ring are up or down. So I'm going to highlight as orange the groups that are up. Can you see that the OH that's a wedge is pointing towards you? Yeah, got that? Okay, everything that's a wedge is pointing towards you. Now let's go look at those carbons, 1, 3, 4, and 5 that have up groups, and let's see whether they are up in the chair or not. How can you tell whether they're up in the chair or not? Two ways. First, as we look at this overhead view of the molecule, we're looking down on the molecule from above. So if we step to the left, or no, right, my other right, the perspective over here is as though we're hovering and looking down at the molecule from above. So where the eyeball is up. The second way you can remember is to use the term equatorial to remind you of a globe, and imagine that the ring is at the equator of the globe, and up is the North Pole where Santa Claus is, all right? So up is towards the top of the page from the chair perspective, down is towards the bottom of the page. So one by one, the OH group on carbon 1 is what? Is it up or down? Up. Okay, equatorial ones are still angled up. This equatorial up carbon, getting that wrong. This is what we would call an equatorial up substituent. This, on the same carbon, is what we would call an axial down substituent. Okay? The equatorial substituents, when they point up, they're going to be angled up towards the top of the page, but not pointing directly to the top of the page. An axial up substituent, like this hydrogen, is going to be pointing towards the top of the page. So carbon, let's see, the other OH groups that were up were on carbon 3. Is that group up? Sure. Yep, angled upward. How about 4? No, do you see how that's pointing downward? It's leaning downward. So I'm going to highlight that in pink. Do you see that that's not the same? It's up here, but it's down here. So even though this group was right, and this group, was right, we found a mistake. Those are not the same compound, okay? I'll just highlight the rest of the groups on the molecule. The hydroxymethyl group that's on carbon 5 is also up in our drawing here. And then this OH on carbon 2 that is down is also down here. So if you go around the ring, we have correct up-down relationships all places but one. Those are not the same molecule. So it would be incorrect to select that option on the right as being the most stable chair of the molecule that we drew on the left, because it's not the right molecule. In fact, it has a different name entirely. The molecule on the right is called beta-D-glucopyranose, or glucose. The molecule on the left is called galactose. They have different uses in biology, different properties, all because of that one OH group that's up in galactose but down in glucose. Yeah?
So if there's a wedge on the molecule, then we're supposed to know that the substituent space is up.
If there's a wedge on a cyclohexane ring, yeah, you're supposed to know when you draw the chair, it should be up. Yep. Go ahead.
On the glucopyranose, you're saying that on carbon 4, the hydroxy group, you know it's down just because of the pattern of the stationaries that goes around the ring?
Yeah, you know that it's down. The equatorial substituents are tricky. They alternate up, down, up, down. Equatorial positions will alternate up and down on alternating carbons. You know it's down because it's angled towards the bottom of the page. Yeah. Okay. So, yeah, go ahead.
When you say like anything's up or down, it doesn't have to be like vertically up or down, just anything more or less than horizontal?
Right. Up or down, it needs to be more or less than horizontal. It doesn't need to be pointing straight up. Okay. There are two kinds of up groups on a cyclohexane ring. One is axial up. That's this hydrogen here, axial up. And then one is equatorial up. Equatorial is going to be splayed out to the side, but still angled upward. Go ahead.
So if that OH group was up instead of down, it would be the same, right?
Right. So that's just what I was going to ask. If you took this molecule, how could we, oops, that's not what we wanted. How could we alter it so that it would be the correct chair? And the answer is you find the substituent that's wrong, and then, yeah, you switch it to be up. Now at carbon 4, which is at a peak, the up position is axial. And so now we've got the correct thing. Now this is a chair conformation of the right molecule, okay? So I'm going to use a triple equal sign to indicate those are the same thing. Yes? Great question. So how do you know whether a group, if you know a group's up, but how do you know whether it should be axial up or equatorial up? And the answer is that for any cyclohexane ring, there are going to be two possible chairs to draw. You're going to start with one of them, and then you can draw the other. And What I mean by start with one of them is I have to choose whether carbon 1 is going to be at an up carbon or a down carbon. I think Nate told you this. In a chair conformation, you have carbons that I'm going to highlight in pink that are at valleys. I call those down carbons. You can call them valley carbons if you want. And then there are carbons that are at peaks, and I call them up carbons. At up carbons, the substituent that goes up is axial, and the substituent that goes down is equatorial. On a down carbon, the substituent that is down is an axial down group, and the substituent that is up is an equatorial up group. So the reason I'm reminding you of that is just to say that when I drew this molecule, I chose to put the oxygen at an up carbon position, and that made it so that carbon 1 was at a down carbon or valley carbon position. That made the decision for me because this OH group is a wedge. The only up position I have at carbon 1 is an equatorial position. Now, you could have asked, what if I started with the OH group with the oxygen of the ring, at a valley position? I would continue to number carbons 1, 2, 3, 4, and 5. Now on carbon 1, that is at an up carbon position, what is the up substituent? It should be axial or equatorial? Axial, has to be. So the decision I make about where to start, and whether that's at an up carbon or a down carbon, determines whether everything else is going to be axial or equatorial. So I could go along on carbon 2, that's a down OH group. So on this down carbon 2, the down position is axial. Carbon 3, axial up. Carbon 4, equatorial up. And then carbon 5, axial up. Again, notice that all the up-down relationships stay exactly the same. But what was axial became equatorial, and what was equatorial became axial. And the molecule, it just so happens that the one we drew at the first is the most stable chair because it's got the most stuff equatorial. Yes?
So overall, whether it's up or down is decided by whether it's a wedge or a dash on the original molecule?
Yep, whether you draw a substituent up or down is determined by whether it's a wedge or a dash on the original molecule.
And then you decide if it's axial or equatorial based on if the carbon is peak or valley.
That's right, you decide whether it's axial or equatorial based on whether the carbon's at a peak or a valley. Now, go ahead.
So you said it's more stable because it's the most stuff that's equatorial.
Most stuff that's equatorial.
Does that depend on molecular weight? So obviously if you flip up, like you got rid of all those hydroxyl groups or something like bromine or something.
Sure. How do you determine whether a group should be axial or equatorial preferentially? Those were the A values that Nate talked to you about last time that give you a quantitative measure for how much worse it is for a different kind of group to be axial versus equatorial. So you can make that comparison directly. It doesn't actually track with molecular weight because bond length matters too. But yeah. Okay, so students often ask, what if I draw the wrong chair at first? And I say, don't worry, just then draw the other chair, which sounds ridiculous, but it's important because we could very well have started with this one. I could totally have decided to put the oxygen at a valley position, and that would have determined that all of these groups were axial. And then I would have looked at that and said, okay, I need to draw the other chair. And this should be a review, but when a chair flips, the following things happen. and this is good to practice because you don't want to misunderstand this. Some people don't understand this at a deep enough level and they get things wrong. So when a chair flips, an up carbon becomes a down carbon, and a down carbon becomes an up carbon. In other words, peaks and valleys switch of the carbons, okay? The third thing that happens when a chair flips is axial substituents become equatorial, and equatorial substituents become axial. Look at what we just did with chair flipping. The OH group on carbon 1 that was equatorial is now axial. And look, carbon 1 that used to be at a valley position is now at a peak position. However, for the substituents, up substituents stay up. Up and down for substituents does not switch for chairs, and down substituents stay down, okay? You gotta get all 6 of those to do this correctly. All right, other questions? Yes?
Just to clarify, because when we're doing like, if you visualize it, it's like, we call it like ring flipping, right? Where you put
Yeah.
it down and go up. It seems like you do also kind of rotate our perspective because of the oxygen, is that?
Sure. So one question that's often asked is, when I draw a chair flip, does it matter how I draw the ring? For example, your text may show something like this. Ooh, there's a chair, and then we flipped it, and then it looks like this. That is mostly marketing, by which I mean the text is trying to communicate that there's been a change, but drawing the 2 chairs that way, to me, doesn't really do anything. Let me just give you a quick example of that. Here is a cyclohexane ring in Spartan. Here we're looking at it, and you can see that the chair is sort of slanted to our left. Got it, right? To make it slanted to the right, I don't actually have to do a chair flip. I just need to twist the ring around a little bit, right? So to me, drawing it this way versus that way doesn't communicate chair flipping, because I can simply step to the left or step to the right. I'll just illustrate that in our drawing here. For example, let's look at this more stable chair of galactose. If I redraw the chair like this and I keep putting that oxygen at a peak position, nothing has changed. Oops, I needed to draw that this way. Nothing has changed. I've just changed where I was standing when I'm looking at the molecule. So you can feel free to change the slant of the chair to remind yourself that you're flipping the chair, but the thing that really flips the chair is those things. Yes?
So 5 and 6, substituents stay up and stay down. Like, what are you referring to?
I'm saying the OH group on carbon 1, that is a wedge in this drawing, is pointing upward here and is also pointing upward there. Yeah. Yes?
When you're drawing the original chair confirmation, how do you decide what's equatorial and what's axial? I know doesn't that alternate? Like,
When you're drawing the original chair conformation, how do you determine what's equatorial or axial?
yeah, is it based on the wedges and dashes?
Yes, it's based on the wedges and dashes, and then which carbon you choose to start drawing on. Let's just put it this way. In general, let's make it real easy. Let's just put a methyl group and another methyl group. Let's do 2. 3, 4, 5, 6. If I choose to start numbering carbon 1 at a peak position, then the methyl group on carbon 1 has to be axial, and the methyl group on carbon 2 has to be equatorial.
Is 2 is that a valley?
Yes, 2 is a valley. Yep. Peaks and valleys alternate. Alternatively, I could have chosen to start numbering 1 at a valley and 2 at a peak. And if I did that, then it would have to be equatorial axial. Yeah.
Because it alternates between peaks and valleys, that's why it alternates between axial.
Right. Up substituents, because the carbons alternate between peaks and valleys, the up substituents also alternate between equatorial and axial.
So if it's at a peak, then it's going to be axial, and if it's at a valley, it's
If an up substituent's at a peak, yes, it'll be axial. If an up substituent's at a valley, yes, it'll be equatorial. Good. Yep. Others, yeah.
So this is kind of dumb, but how do you like identify a peak and a valley?
Yeah, so how do you identify a peak or a valley? If you look at a chair from this direction, the peaks are the ones that are pointing up towards you, and the valleys are the ones that are lowered away from you. If you look at it from the side, the peaks are at positions where it looks like they're a V, but upside down. And the valleys are at positions that the 2 carbon-carbon bonds are pointing downward.
So looking at that on the plane of the page, could it technically be anyone?
So if you're looking at it from above, you can't tell,
Yeah.
which is why I'm saying when you draw the chair, you got to make a choice. Put carbon 1 at either a peak or the valley, and then draw it, and then do the other chair by putting carbon 1 at the other one. Yeah.
Or response then. It just
Yes.
It just has to be, they have to both make sense together.
That's right.
Peak and valley, okay.
Yep. Yes.
So like if you have a cyclohexane with 6 carbons, and you have 3 equatorial and 3 axial, how do you know which is stable, which chair?
So if you have a cyclohexane ring with 6 carbons, and then
Like in terms of stability, like which, because it's more stable with more equatorial groups.
right, so deciding what the more stable chair is depends on the sizes of the groups. You learned something last time, I think, which was that these are 2 different chairs of the same molecule, and the equatorial conformation is more favorable than the axial conformation, and the change in free energy was something like 1.6 kcals per mole or something like that. And we called that the A value. That is the penalty for having a methyl group axial. And I think Nate gave you a list of A values for substituents that you could determine whether it was better or worse for various groups to be axial versus equatorial. Quick example would be to say, okay, what if I had a cyclohexane ring that looked like this? Let's put a T-butyl group here. You want to do this? Yeah. And then a methyl group there. So let's draw the most stable chair conformation for that molecule. Again, it'll maybe be best to just number around the ring, then draw a chair. I'm going to choose to put carbon 1 at a valley, 1, 2, 3, 4, 5, and 6. Now that I've made that choice, on carbon 1, the methyl group is up, and my only up position on carbon 1 is equatorial. Then on carbon 4, that T-butyl group is up. And now I come here, the only up position on carbon 4, which is at a peak, is axial. So this is axial up. Now, the A value for the T-butyl group is like 5.7 kilocalories per mole. So that's the penalty for having the T-butyl group axial. Now I'm going to draw the other chair. I can do this any way I want other than the peaks. Peak carbons have to become valley carbons. So that means I'm going to put 1 here at a peak, 2, 3, and 4. In the other chair, the up position on carbon 1 is now axial, and the up position on carbon 4 is now equatorial. The penalty for having a methyl group axial is only 1.7 kilocalories per mole. So it's better to have methyl be axial than to have T-butyl be axial. And so we can make the decision that this is the better chair. Yep. And you can do that, you can deal with A values mostly additively. There's the word, right? Additively. So that's why we made the decision up here, you know, having 1, 2, 3 hydroxy groups and a hydroxy methyl group equatorial and only 1 hydroxy group axial was better than having 4 of those axial and only 1 equatorial. Yeah?
You don't want us to memorize the A values.
No, you don't need to memorize the A values. I happen to have them in my head mostly. I'm probably wrong to one significant figure or whatever, but yeah, you'll have a table. Yep. Okay. So practice that. I don't want anybody to get the question wrong where I draw something like this. And by the way, just like think through things rationally, right? If I draw a molecule like this and I say, which of the following is the most stable chair of that molecule? How many chairs does a molecule have? 2. So if there's options A through H, most of them can't even be the right molecule, right? So don't get fooled. Make sure you get the up-down relationships correct. Now, these 2 molecules are isomers of each other. They have the exact same connectivity, but their shape is different, and they can't be interchanged by rotation around single bonds. So because of that, they're a particular class of isomer called stereoisomers. I see a hand. Yeah, go ahead.
Right, is it those 2 or is it the 2 chair conformations that are isostereo?
No, the chair conformations are not stereoisomers. They are conformations of the same molecule because you can interchange them just by rotating around carbon-carbon bonds. But I can't interconvert glucose and galactose without physically breaking a bond and sticking it back on the other side. So those are called stereoisomers, and that's an important term, and we need to go through that. Now, I've heard that you talked about this a little bit in Gen Chem, but I heard that you talked about it very quickly. There was like a review sheet you were supposed to know, and then there were questions on the test, and it was really hard. Yeah, okay, that described your experience. So we're going to explain it a little bit more. You won't need a review sheet, and then there will be questions on the test, and it will still be hard. So I don't know if your life has improved at all, but we're going to go through, and I am going to disclose all my evil tricks and show you how to deal with them. So stereoisomers, again, same connectivity, not the same thing, not the same molecule, and importantly, not interconvertible by rotation around sigma bonds. So if you can interchange 2 things by chair flipping, they are the same molecule. All right? Now, let's see. So there are 2 kinds of stereoisomers, and only 2. All stereoisomers have the same connectivity, but are not the same thing. But there are 2 different classes of stereoisomers. The first is stereoisomers that are mirror images of each other. But again, not the same thing. That's true for, not being the same thing is true for all stereoisomers. So molecules that are mirror images of each other but are not the same thing are called enantiomers. And then all other stereoisomers that are not mirror images of each other but are also not the same thing are called diastereomers. So we only have two kinds of stereoisomers. Either they're mirror images and not the same thing, in which case they are enantiomers, or they are not mirror images and are still not the same thing, in which case they are diastereomers. You have already encountered diastereomers, but you did not know it at the time. Your first example of a diastereomer in this class was the idea of cis and trans, or E and Z, in alkenes. Notice that they have the same connectivity, but different shape. Notice that you cannot interchange the two of them by rotation around sigma bonds. You can't rotate around pi bonds. So those are two different molecules, different shapes, same connectivity. They are not mirror images of each other, and therefore they have to be diastereomers. Okay? Yes?
When you say mirror images, does it have to be in a specific, like, plane, I guess? Like, does it have to be a mirror image of the y-axis or the x-axis?
No, when we say mirror image, we just mean in general. So if you can find a mirror plane, then that's good. Yep, then it counts. So those two are not mirror images of each other, so they're diastereomers. And in general, all cis-trans issues in organic chemistry are going to be issues of diastereomers. Another example of diastereomers would be this one. These two molecules. One of them, in the one on the left, the methyl groups are cis to each other. In the one on the right, the methyl groups are trans to each other. Again, these two are not mirror images of each other, so they have to be diastereomers. And why do we care about that? Well, diastereomers have different chemical and physical properties. They do different things at the level of boiling point and melting point. They are different. They do different chemistry. You expect them to be different in most respects. In contrast, enantiomers are going to have the same chemical and physical properties, with two exceptions. And those two exceptions are, first, how they interact with light, and I'll talk more about that in a little bit. And second, in biology. And there's reasons for why biology is special and why enantiomers don't have the same biological properties that we'll talk about a little bit later. So, figuring out what the relationship between two molecules is, whether they're enantiomers or diastereomers, is important because it allows you to calibrate your expectations about what's going to happen. All right, are there questions about those definitions? Those are words that describe relationships between two molecules, so it makes no sense to say, is this molecule an enantiomer? It's like asking you, are you a sister? Of whom? Am I that person's sister? Yes. Am I that person's sister? No. It depends, right? So you have to talk about the relationship between two molecules. Are they enantiomers? Are they diastereomers? Enantiomers have a property called chirality, because chirality means that chirality means you are not the same as your mirror image. So that didn't make sense. I'm using a noun when I wanted an adjective. Enantiomers are always chiral. Chirality means not being the same as your mirror image. Diastereomers might be chiral or they might not be chiral. And we'll talk about that a little bit later. Okay? Enantiomers are always chiral. Diastereomers might or might not be. Now, chirality is, go ahead.
Can you give us an example of an enantiomer?
Yep, going to right now. Yep. Chirality is embedded in the very fabric of the universe. And you have daily experience with it, though you might not appreciate it yet. So the easiest is your hands. Your right hand and your left hand are mostly mirror images of each other. If the mirror is the interface between the two, they look like they're the same, but they're not the same. You can tell they're not the same first because some of you are left-handed, some of you are right-handed. I can't get my left and my right correct on the first try, for some strange reason. You know that if you're right-handed and you try to write with your left hand, it doesn't go very well. So for example, here is my left-hand benzene ring. Ugh. I'm trying really hard. I feel like a 5-year-old. All right, so they do different things. Second, you can try to flip them over and line up all the fingers correctly, and the thumbs, you can line up the palms and the backs of the hand, but then the fingers don't line up. You can line up the fingers correctly, but then the palm of the hand and the back of the hand don't line up. They're different, right? The other experience you have with chirality is if you've ever looked in the mirror and then seen a picture of yourself and thought about the picture of yourself, who's that guy? Because that's not what I look like. And then you come to your horror to realize that that's actually what everybody else sees when they're looking at you, right? That mirror image of you is not the same as you. It's your enantiomer. And you know, if you want to have some fun, you can actually, to demonstrate that you are chiral, you can take one half of your face and try to show what you would look like if you were perfectly symmetrical, and it would be weird. You'd look at that, you'd look at both of those halves of your face put together to make a whole face and be like, whoa, okay, that's also not me. Okay, so chirality is embedded in the fabric of the universe, and we're going to talk about where it comes from at the molecular level and how you can tell when two molecules are not the same. And we'll eventually get to why it is that you are chiral, and at the molecular level, it's because you are made of chiral molecules. We're also going to talk about what happens when two chiral molecules interact with each other. But just to illustrate the point, if you've ever been in some kind of interview with a mission president or a stake president or a future employer or whatever, and you go to shake hands, you probably follow which hand they shake with, right? So if they put their right hand, you probably shake it with your right hand, right? What happens if somebody goes to shake you with your shake your right hand, and then you offer your left hand? Suddenly you're like, oh, Shantae, right? Like, it feels kind of weird, right? That's because two chiral things can tell the difference between each other, right? You've got sort of awkward versus firm handshake. In the same way, biology can tell the difference between chiral molecules. But before we get there, let's demonstrate the concept of enantiomers and not being the same as a mirror image. And we're going to do this with a very simple molecule. And the molecule is this. So here is a hydrogen, here is a carbon, here's a chlorine, here's a fluorine, and here's a bromine. I'm not sure if this is a molecule, real molecule. I don't know how stable it is. We're going to highlight 4 different groups on this molecule. All right? And the question that you might be asked is it chiral? And to answer that question, you have to say, is it the same as its mirror image? So we're going to use a dashed line to draw a mirror plane, and then whatever we draw on the right side of the line has to be a reflection of what's on the left side of the line. So here is your hydrogen. The chlorine, which was angled down towards the bottom of the page but pointing to our left, must now be angled towards the bottom of the page but pointing to our right. Secondly, the fluorine, which used to be a wedge pointing downward towards our right, must now be a wedge pointing downwards towards our left. And then similarly, the bromine needs to be here. So first thing to get good at is drawing the mirror image of a molecule. You have to be able to conceptually imagine putting a mirror in between the two and drawing on the left-hand side of the mirror the same thing that's on the right-hand side or vice versa. Okay, so that's skill number one. Skill number two then is convincing yourself whether those two molecules are the same or not. And to do this, it's useful to build models and play with it, or you can try to develop some on-the-paper molecular manipulation skills. So let me show you one of these. Behold, the claw innator. All right? The claw innator grabs a portion of the molecule and holds it steady and then spins the molecule around 180 degrees. So let's do the claw innator operation and then redraw the molecule. The hydrogen was held in place by the claw. The rest of the molecule was spun around. That would put chloro here on the right. And so far, I'm feeling pretty good about life because it looks like, they're going to line up, right? But what happens to the fluorine that used to be a wedge? What is it going to be now? Dash, because I've spun it around. And the bromine, which used to be a dash, is now a wedge. So I can get the hydrogen and the chlorine in the right places, but I can't get the fluorine and the bromine in the right places. Okay. You say, why not try flipping it over again? Let's actually take the claw innator and put it here, and let's take the fluorine and the bromine and spin them around 180 degrees to interchange their position so that they will line up appropriately. Okay, fine, we can do that. Fluorine comes back here. Bromine comes here, but what happens to the hydrogen and the chlorine? They're switched. So you can play around with the claw innator until the heat death of the universe, or until the earth is celestialized and we all enter into our glory, and those are still not the same thing, ever. Worlds without end, all right? So you've convinced yourself that they are different. They are not the same. They are mirror images of each other. Therefore, they are enantiomers. And each of them has the property of being chiral. Now, there are a lot of ways to be chiral, but one of the most common ways is to have one or more stereocenters. A stereocenter is a carbon, and I'm going to define it somewhat narrowly. Nope, that's not the word. I'm going to define stereocenter a bit more narrowly than the actual definition is. It'll work for us in this class. A stereocenter is an sp3 hybridized carbon attached to 4 different things. So you're going to need to get good at identifying stereocenters. There's a stereocenter labeled in pink on the left. There's one on the right. Now you see a nomenclature problem. If I were going to name these two molecules that are not the same thing, they're both bromochlorofluoromethane, but that name alone doesn't distinguish which enantiomer I'm going to have. And so I need a way of talking about these two enantiomers, and that's where the R and the S stuff come from. We'll talk about how to do that, but not right now. Stereocenters are important because they are useful tools in identifying whether a molecule is chiral or not. If a molecule has only one stereocenter, it must be chiral. If a molecule has two or more stereocenters, it might be chiral, but it might not be, and you have to check. Let me give you an example of a molecule with stereocenters that is not chiral. In fact, you've already seen it today. Behold, 1,2-dimethyl cyclohexane, cis 1,2-dimethyl cyclohexane. Carbon 1, carbon 2. In deciding whether a stereocenter, a particular carbon is a stereocenter, we're going to use the exact same standards for differences that we use to assign E or Z. In other words, two groups are different if you can find a difference in either the atom or what they're bonded to out as far as you can go. So, for example, carbon 1 is bonded to a hydrogen and 3 carbons, but those 3 carbons are not identical. That's pretty easy to see here. One of them's a methyl group, one of them's a CH2 group, one of them's a tertiary carbon. Do you see those differences? So carbon 1 is a stereocenter. Similarly, carbon 2 is a stereocenter. Now, is it the same thing? Well, let's draw the mirror image. And then we will use the claw to twist the molecule around 180 degrees, and it's the same thing as its mirror image. Do you see that? So this is a molecule that has stereocenters, but is the same as its mirror image, and is therefore not chiral. Molecules that have stereocenters but are the same as their mirror images and are therefore not chiral are called meso compounds, and I'm not sure why they're called that, but meso compounds are the worst because it's easy to be deceived. And I have a lot of ways to conceal meso compounds from you. For example, at some point you're going to realize that in general, one good way to potentially draw an enantiomer is to switch all the dashes and wedges in a molecule. And that works except for meso compounds. You might look at that and say, oh, you switch the configuration of the stereocenters, therefore it's an enantiomer. Why am I wrong here? What operation do I have to do to demonstrate that these two are the same thing? Ah, yes, behold, the pancake flip-inator, also called the molecular spatula. Slide your spatula under that thing, flip it over, it's the same thing. So you must get good at manipulating molecules on paper and in your head so as to detect the evil meso compounds which look like they're chiral but actually aren't. Okay, we'll pick that up Wednesday. Have a good day.